Welcome, everyone. This is the last Talk Math with Your Friends of spring 2022. I still think it's like 1997, but I'm really excited that we have Bolanle Salaam, or Lonnie. She's a graduate student, I believe, at the University of Georgia, and she's gonna tell us a little about some exciting ways that she has at getting at student thinking that seem really novel and productive, both as a researcher and as a teacher to me. And so please join me in welcoming, well, I say future Dr. Bolanle Salaam to Talk Math with Your Friends.
Thank you so much for the introduction. Thank you all for coming to this talk today. I decided to make it as interactive as I could possibly make it. I, in particular, work with undergraduate students, students in their first year of their mathematics major, are the students that I study. And I wanted to just do a little test to see how some of these methods would be applied to maybe like a graduate course, or even looking at something slightly below the students I look at, which is calculus, and maybe trying to come up with some potential issues that might happen in the first week or really the first day of a graduate real analysis course. Thinking about some of the issues students may run into in that course and ways that we could potentially mitigate that in advance. So again, my talk is student thinking through the lens of real analysis, requisite knowledge, the necessity of time, and ways forward. The very first thing that I want us to do, though, is to get an idea of some of the tools that I use in my work. So if you all could just join me on Desmos, you will not have to log in or create an account. You can just join without signing in. So you guys can either go to student.desmos.com and type in the P there, or you guys can try to type the link that I have at the bottom, even though I did also put it in the chat, and Brian has also put it in the chat as well. And I will be looking on my end to see what you guys have done. If you guys can kind of, I see some of you are already jumping forward. If you guys can kind of just focus on slide 2, but please go ahead and read slide 1, which is just talking about the fact that this is recorded. I will be sharing some of your work. So if you do not feel comfortable with me sharing your writing, you can just not participate and not write anything on those slides. But if you are comfortable with sharing, please go ahead and do that. So I'll just quickly kind of read through what you guys will need to be doing on that second slide. You'll be writing something called an evoked tree. There is an example up there. And then I will also introduce myself. So do we have any issues so far with any of you getting in to the Desmos? And I am keeping my eye on the chat. All right, awesome, awesome. Yes, I can see you guys. I love this part about Desmos is that you can see exactly where the students are and what the students are working on. I have anonymized everyone. So when I do share the work, if you have decided to participate, no one will see your name. It will be a mathematician's name. So if that makes you feel more comfortable with sharing, that would be great for me. All right, so the very first thing that I am asking for everyone to do is to draw something that is called an evoked tree in Desmos. So what that is going to do, what you will be doing with an evoked tree is you are given a task. And because we know that the way that a student may respond to a problem is evoked, it's highly situational. Not only is it situational, context also matters. I am not only referring to the problem itself. Yes. So I haven't shared my Desmos yet, but I will, once you guys are all in, I can go ahead and start sharing some of what you guys are doing. So it should still say Desmos on the screen with the link, just in case anybody comes in a little bit later. Okay, so what the purpose of the evoked tree is to just look at the way that students parse problems, particularly what do students notice first? How do they think and realize? So everything that they might notice, we call those signifiers. How do they actually realize those problems that they are looking at in order to coordinate their mathematical discourse to arrive at a solution? And so that is what I will be asking you all to do today. Okay, so what you guys may want to do is if you do agree to go ahead and share with me and you've read the instructions on slide 2, I would ask that you guys go ahead to slide 3, just look at the evoked tree example that's up there, and then you can start to draw one for yourself on slide 4 based on the task that's there. But I will go ahead and start my presentation from here. So I'll really introduce myself at this point. All right. So my background is in pure mathematics. I got my Bachelor of Science degree from Howard University, and I minored in secondary mathematics education. I then went on to get my master's in applied mathematical science from the University of Georgia, and I am currently pursuing my PhD in mathematics education at the University of Georgia as well. So sometimes when people wonder, well, how did I get to student thinking? I tell them that they really need to look at my student engagement background, which is quite lengthy, started quite long ago. So in 2011, I was asked to teach calculus to rising ninth grade students. So these were students who had just left eighth grade. They were now coming into ninth grade, and I was tasked with teaching them limits and derivatives. And we stopped there. Then they went on into ninth grade. And so this is one of the first places that I learned so much about the ways that students think and how to really engage them with some of the more difficult mathematics. I then spent quite a number of semesters as an instructor of record at the University of Georgia, where I taught pre-calculus and calculus mainly, but then I also taught content courses for elementary mathematics teachers. The vast majority of the content that I taught was at an elementary and a middle school level, but we did a lot of why. Why does this work? Why is this true in that course? So I wasn't teaching elementary concepts, but more so teaching the knowledge behind the concepts. I then taught in the high school for 3 years, and I taught pretty much all of the mathematics that they offered. So the lowest level mathematics that we offered was Foundations of Algebra, which actually covered mathematics from first grade through ninth grade. But then I also taught one of our highest level courses, which was AP Calculus AB. And this is where I really started to see just how much or how little sometimes students were getting in our mathematics classes because of pressure, external pressures in the classroom. So we may have had a certain amount of curriculum that we needed to get through, but maybe by the end of the year, there were just certain topics that did not get quite as much attention. Maybe they weren't on the state exam or something of that nature. Maybe there was an assembly that day. So a lot of times we did end up having to go back and teach students particular content in order for them to be successful in the course that they were currently in. But if this is happening all across the United States, we then will eventually start to have some issues when students get to college. Now, my question that I began to ask myself is, does it stop there? Is this just an issue that happens from high school to college, or does it continue from college into graduate school? And from some of the people that I have spoken with, it seems like this is an issue that does continue, and I wanted to understand why that may happen. A lot of the strength that I began to build up in understanding student thinking came when I started to work on grading AP exams. So I would read a ton of AP Calculus students' work, maybe about 1,000 or so, over and over, and you would begin to see patterns in the way that students were approaching the mathematics. And so that then made me question, well, again, what are these patterns and how are these patterns so, I want to use the word odd. So some things didn't really seem to be based in scholarly mathematics discourse, but potentially you would see a lot of students doing these things. And it's something that I also would see in my classroom. So again, how does this happen? So when I got to teaching statistics, I once again saw the same thing. We would do a lot of hypothesis testing problems. Maybe we would ask about, one-tailed left test or right-sided test, two-sided test. And I started to see that those tests were also causing issues for our students. And so again, when I asked students to come to my office and to talk me through the problems that they were doing, I noticed that there seemed to be a discursive element to the way that they were doing the mathematics. And it didn't seem to be based in mathematics at all, but more so in discourse. And so this is how I got into the field that I'm in now, in the field of study that I do. Okay, so my orientation as an educator is that my goal is to eliminate mathematics as a gatekeeper. I see mathematical literacy as a civil right, and I am a true believer in mathematics for all. So whenever I am teaching, I am truly trying to get at the heart of what a student needs, which means that I have to consider their backgrounds before they came into my classroom, even if what I am trying to help them with is not actually the level of mathematics that I have been tasked to teach them. I would like to help their background mathematics as well so they can be successful in my course. Okay. And it's just a really great quote from Alice Walker that also kind of explains how I teach. So she says that I don't know, I imagine good teaching as a circle of earnest people sitting down to ask each other meaningful questions I don't see it as a handing down of answers. And this is pretty much also how I teach as well. So I do not want to be seen as the authority in the room over all the students, just telling them that they're good or bad at math, but as someone who's just had experience with mathematics, and I can maybe give some insight into why I do mathematics the way that I do it. Okay, so before we get into the motivational part of this, I want to go ahead and start to look at some of your evoked trees, if I can share them. Okay, so can you guys see this? Yes, okay, awesome. So I have it anonymized. So I'm going to click on this one person. Okay, guys. There we go. Okay. So here was the task that you all were given. And like I said, we will get back into the motivation for today. So you were tasked with finding the area beneath the curve, f of x equals 5x plus 1, that is bounded on the left by x is equal to 0, and on the right by x is equal to 7. So the example that you all were given was just basically solve x squared minus 2x minus 15 equals to 0, and then nothing else was put there. So like I was saying earlier, this is one of the tools that I use in order to study student thinking. So this particular example is of a student who noticed the word solve and noticed that what they saw on the right-hand side was a quadratic. So how did they get there? So seeing the x squared minus 2x minus 15 equals to 0, they saw that, okay, this is the standard form of a quadratic. It also has these particular coefficients. Wrote out what those coefficients are. They saw the word solving as finding a solution. And they said, okay, well, that means that I'm going to need to use this standard form of a quadratic somehow in order to get me to my answer. I'm particularly used to using the quadratic formula for that. And so this is what you see in their particular tree. Then they coordinated that with those coefficients, did some plugging in, and got down to their answers. So why do I use this in my classroom and whenever students come to office hours? It gives me a way to interrogate student thinking. There are a lot of things that I just said just now that are not represented on this paper. So that means that I'm doing a lot of inference and interpretation on behalf of the student. But that doesn't necessarily mean that that is how the student actually solved the problem. So when I see students make these trees, I tend to ask those questions. What is it that made you write this x is equal to negative b plus or minus? What is that? Where did it come from? Now, of course, a lot of us in here are mathematicians. We've done mathematics. And so we tend to fill those parts in for the student. The issue is that I believe that when we do this, we are sometimes missing out on some of the understandings that students have that may cause them issues down the road. And so this is why I use this thing called the evoked tree. I have to temporarily pretend that I'm not a mathematician and ask students questions about why they did what they did. So now let's look at what you all did. Okay. So this is, I believe, Louis Hugh. Okay. Okay, so it looks like they have area at the top. Okay, area connected to integrals, integrals being connected to functions. Integrals FTC, I believe, again, I have to step into the discourse here. That's standing for fundamental theorem of calculus. Okay, and then that's branching over into antiderivatives. Okay, functions, antiderivatives, combining those to say linear, looking at slope. Okay, area, familiar geometric shapes, awesome, got it. Okay, then we have bounds being x is equal to 0 and x is equal to 7, great. Okay, then also the bound, so it looks like they're considering the function itself as another bound. Okay, beneath, meaning, okay, to the x-axis, great. Okay, I'm seeing a lot of great information. Okay, so it looks like this person carved up their figure into geometric shapes. Okay, and okay, using, from what I can tell here, using their knowledge of geometric areas in order to arrive at their area. Again, this is me stepping into the discourse here. If I had a student doing this, I would be asking a lot of questions about how they are arriving here from what they saw in the problem. Okay, we have another person. Okay, so it looks like another person who's attempting to draw the picture, finding the area, paying attention to what the actual function is and that it's bounded, great. Okay, very similar things again. All right, so we have here our interval that we're working with, again, area underneath the curve. Yes, so a lot of times when I ask these sorts of questions to people who are within mathematics, we see a lot of similarity in how the mathematicians actually go about these problems. The things that when we start to ask students, we begin to see some things that are particularly interesting even for us. And I really like to not tell students, where is this coming from? That doesn't make sense. I think that that is an opportunity to ask them, can you help me to make sense of what you did? And then we start to see some really brilliant things that our students are actually doing, things that actually may be mathematical, but that we just couldn't see, or things that maybe do not seem to be mathematical that we can assist them with. Okay, it seems like somebody knows the anonymous mathematician that they got. Okay, great. All right, great. So that's just one of the tools that I use. All right, so you guys have drawn your evoked tree, the highly situational one. But now let's talk about why I actually asked you all here, how we're going to look at student thinking through the lens of analysis. And so I will read you some of that section of the Rudin that I asked everyone to read, and then we'll try to deconstruct what's going on there. But thank you all for helping me out with that evoked tree. So keep that in mind as we go forward for the rest of the day. If you guys had any issues with drawing those trees, or if any of it was kind of confusing to you, you can just go ahead and put that in the chat, and I'm going to reshare the slide here. Let's make sure it's there. Are y'all seeing it? Yes. So that's why. So someone mentioned that they wanted it to be arrows. No problem. So there was a way for you to draw so that you could put the arrows on the ends yourselves. Yeah. There's some features of Desmos that I wish just had a little bit more to it. And I love that you said that, because mathematicians and people who do mathematics always want to put arrows on these things. They always want to indicate direction, and students never seem to want to, but it just seems like this is something that mathematicians naturally do. And there's a reason for that, which I'll get to later. All right, so the motivation for today. All right, so this is the page that I asked all of us to read in Rudin. So this was the homework. Okay, so I will just read through this, and just anything that you can kind of pick out while I'm reading it that allows you to form an image in your mind of what is actually being talked about here. You might want to just hold on to that, because I will have you put it into Desmos as well. All right, so toward the end of the 19th century, it became clear to many mathematicians that the Riemann integral, about which one learns in calculus courses, should be replaced by some other type of integral, more general and more flexible, better suited for dealing with limit processes. Among the attempts made in this direction, the most notable ones were due to Jordan, Borel, W.H. Young, and Lebesgue. It was Lebesgue's construction which turned out to be the most successful. In brief outline, here is the main idea. The Riemann integral of a function f over an interval a to b can be approximated by sums of the form summation from I is equal to 1 to n, f of t sub I times measure of e sub I, where e sub 1 up to e sub n are disjoint intervals whose union is from a to b. Measure of e sub I denotes the length of e sub I, and t sub I belongs to e sub I, where I is equal to 1 up to n. Now, I didn't want to stop there. There was a more natural place to stop, so I did go ahead and continue with the rest of what they were trying to discuss there. Lebesgue discovered that a completely satisfactory theory of integration results in the sets e sub I in the above sum. Satisfactory theory of Lebesgue discovered that a completely satisfactory theory of integration results if the sets e sub I in the above sum are allowed to belong to a larger class of subsets of the line, the so-called measurable sets. And if the class, it's so many years, and if the class of functions under consideration is enlarged to what he called measurable functions, the crucial set theoretic properties involved are the following. The union and the intersection of any countable family of measurable sets are measurable. So it is the complement of every measurable set, and most important, the notion of length, now called measure, can be extended to them in such a way that the measure of the union of e sub 1, e sub 2, and so on is equal to the measure of e sub 1 plus the measure of e sub 2 plus the measure of e sub 3, and so on, for every countable collection e sub I of pairwise disjoint measurable sets. This property of M is called countable additivity. The passage from Riemann's theory of integration to that of Lebesgue is a process of completion in a sense that will appear more precisely later. It is of the same fundamental importance in analysis as is the construction of the real number system from the rationals. So I'm just looking at the chat where someone is saying they haven't done this in so long and that their head hurts. And this is why I want to really talk about it. So when we're reading Rudin, at the beginning, it does say that this book is really supposed to be accessible for people who are in their first year of graduate school. So if it's written at the level of a first year real analysis course. And even in this little excerpt that we read, again, this is the first true page of the book after the like the pre-material. So this is supposed to be accessible. All right. The question is it? Do we expect this to be accessible to someone who is in their first year of graduate school? And are there any particular types of students who may find this inaccessible? So that is what I wanted to think about. And I ended up having some questions when I read this. So considering that the student reading this text is in their first year of graduate school in a mathematics PhD program, let's try to answer these following three things. What is the highest level of mathematical content that you believe a student will need to be familiar with to follow that introduction? In what prior courses do you believe that a student should have gained familiarity with the content that you have identified in response to the last question? And last, what connections do you anticipate a student will need to make to K through 16 content to make sense of that introduction? What connections do you make to prior K through 16 content to make sense of this introduction? So I do have a place for you all to do this. Okay, I do have a place for you all to do this in your Desmos. You will see 3 boxes where you have these exact questions, and you guys can go ahead and just type what you think about it there. And then I'll read some on my end. If anyone wants to share out publicly, that also works as well. So just take some time to think about that. If you do want to say something, I guess you can raise your hand. But I would love if you guys could also maybe put it in Desmos. If everyone gets the questions up, I can put the excerpt back on the screen if anyone would need to see that.
For the first question, I'm thinking that you need not just a real analysis class, you need a very special kind of real analysis class that problematized the sort of topology of the real line. So if you ended that class with the idea that like, yeah, for really nice stuff, this works out, but in grad school, you're going to do this again, then I sort of like this in the same way that I like Dumbit and Foot, where it starts with the whole like, so you know about great rings and fields and all those things, let's do modules and do all of it together better. But it only works under the assumption that you already understand that that's a question worth asking. Okay, got it. So like, why is this even necessary? Right. Why are we generalizing? Didn't it work last time? Right, got it.
Well, so, I mean, I'll put this in my thing, but I just wanted to bounce on what BK said. So to me, it's not really an issue of content at all. It's like, you know, or understanding why there's a problem. It's being able to put yourself in a position to demand things of mathematical objects. Like it's, to me, I mean, like, you know, reading it, what you need to know what sigma notation means. That's about it, right? And like what union means. Okay. But those are fine. Those are relatively low level, but most students who have those are not going to be able to handle this because they have never thought of themselves as being in the driver's seat of saying, I'm going to make up a new definition that satisfies me.
Love it. See if we have others. I'm going to temporarily, to see some of the things that you guys added. Sorry. There we go. So 1 second, let me pull up. Sorry guys, there we go. Your work is not showing up for me. 1 second. There it is. Okay, so I'm going to pull some of these over so you guys can see what some people are saying. There we go. All right, so I guess we'll just go in order and I'll just read out some of the things that you all said. All right, so what is the highest level of mathematical content that you believe a student will need to be familiar with to follow this introduction? Okay, it helps if you already know the content of this book to undergo the entire content, okay? Okay, so measure theory, so measurability does get discussed after that page. So it was like a little kind of introduction into the entire book, yes. But I guess what I want you all to think about is what are the parts that they are assuming? So the measurability part is the subject of that chapter that comes right after. Okay, so when I see real analysis, are we talking about real analysis at the graduate level or real analysis at the undergraduate level? Okay, signal notation, unions, introducing the idea of measure requires some generalized length, okay? So courses where definitions and ideas are generalized, okay, awesome. Integration, discrete math, got it, okay? So those are like our collegiate level classes, awesome. Okay, so in what prior courses do you believe that a student should have gained familiarity with the content that you have identified to question 1? Undergraduate real analysis, that highlights the topology of the real line, okay, great. Graduate real analysis, okay, some kind of course where axiomatics are introduced, okay? Certainly undergrad analysis, okay? Multivariable calculus. So the reason why I really am stopping on this answer is that in that little passage that I read, they start talking about Riemann integrals as being something that's introduced in calculus, right? All right, so let's see. A goal-oriented, okay, so connections. How do we go from algebraic functions to piecewise, generalizing our strategies? Calculus and real analysis, okay. How does length work? Awesome. Some sort of coursework where definitions are generalized, awesome. Transitions in human history, okay, I see. So really motivating what's going on here. Awesome, awesome. I like it, I like it. I don't think it's an issue of content. Okay, it's a question of positioning ourselves to demand something from, okay, so yes, I said earlier, Peter, trauma, okay. Some people say that they have trauma from learning measure theory. Okay, awesome, awesome. That requires a serious prior experience and content problematized in previous courses. Okay, okay. So one of the questions that I wanted us to also think about here were what kinds of students may struggle just reading that? So remember, this is something that if it's a student who maybe is self-teaching, maybe they don't really do so well with professors and they prefer to go home and read the book. And remember, this is a student who they have just started graduate school. Can we anticipate any possible issues? Does anyone want to share out there? I would love to hear thoughts. Because one of the reasons why I really wanted to kind of look into this is sometimes we speak about students who get to graduate school in mathematics as though they no longer have the issues that students in K through 12 and in undergraduate have.
I mean, I think basically all students or a very large number of students trying to read this are going to have, you know, in this population are going to have trouble. Mm-hmm. Just because they're not, I mean, this is probably not something that they're ready to do. I mean, so when I teach a class like this, I will have to spend a lot of time in person with students, like convincing them that it's okay to, you know, think about something very easy like length.
Yes. And
then to try to generalize it to something that's, you know, at first blush seems extremely abstract.
Right, right.
And kind of making that big sort of leap of faith of like, yes, it's okay for you to say, I want, you know, these 4 axioms to be satisfied just because I want them.
Right.
Like everybody struggles. I mean, I don't know, maybe there's people, I did.
So even if we say that a student is well prepared for graduate school, we're still expecting them to struggle with accessing this introduction as well?
Yeah, I think so.
Is there anything we can connect to? Is there anything that we expect students to maybe notice or something that they should have learned before that maybe can help them access this in what we read?
We have a hand from Gabby.
Yes.
I can like share my experience. I like met a professor from Colorado College who said that it's only the 3rd time when you take real analysis that it starts to make sense. And I agree with that so much. Like, not just like real to complex to like 3rd course being in measure theory. It's like 3rd time taking real analysis in undergraduate, at the undergraduate level, and it's really like I took it like just 18 months ago, and it was a really difficult time to like get adjusted to epsilons and deltas. And I think it also depends on how your undergraduate program is shaped, because at my college they only offered like 1 semester of real analysis, whereas other universities I heard people were taking 2 semesters real analysis before starting on to measure theory. And I actually enrolled myself in measure theory at my semester abroad in Budapest, and people from other universities were so much more comfortable with the lingo than I was, because they had more experience. Like they had two big semesters of just real analysis to back them up. So yeah, it was difficult.
Was there, I think someone else was about to say something.
Oh, yeah, I also had a very calculus-based real analysis class. And then the next year I graded for real analysis and a different professor taught it. And she did a measure theory approach. So in some ways I had this experience where I wasn't going to class and I had to figure out what the heck was going on. But in terms of your other question about what we could do, one thing I was thinking about is if I were to ask my master's students to say things like, okay, explain how we approximate areas in calculus, and I could get them to explain this sort of a narrative that feels like this, and then we could correlate the pieces of their story to this story, and then we could start thinking about the assumptions that they needed for theirs to work out, and think about how those assumptions might not always be true, so we might want something more general. So I would sort of start from something they know from calculus, especially since many of my students are future teacher or are teachers who maybe teach calculus. So they have some ways of explaining like Riemann sums as approximations.
Yeah, and I find this very interesting. I actually really felt like more people would seize on the Riemann integral part, because that is actually content that is currently on the AP Calculus exam. So students who take that class in high school are supposed to be familiar with what is being described there. They quite literally do have to sketch Riemann sums, and they do learn the actual meaning behind the integral symbol. So when I actually read this, the reason why I chose Rudin, let me just go ahead and say that. The reason why I chose Rudin specifically was because so many mathematicians love it. And so I'm thinking, well, if mathematicians love this book, and you're going to assign it to your students. So I said so many, not everyone. so many. So this is one book that, so like even hearing Dumb and Foot, there are just certain books, or Thomas for Calculus. There are certain books that I constantly hear mathematicians refer to. And if these are people who are teaching, okay, so I will go to Melfi, who are teaching these universal revulsion, oh my gosh, who are teaching these graduate courses, if they are assigning these books that it seems like we feel are not accessible, am I maybe misunderstanding the sentiment in the room regarding just this first page?
Well, this is maybe a biased sample. The people who would come to this colloquium are maybe the ones who are very student thinking centered in the math community.
Well, so I never used Big Rudin. I never used this, right? But I had Baby Rudin, and this is a lot more discursive than like anything that's in Baby Rudin.
I see.
So I like this a lot. This is nice in comparison. So
and so it's funny because when I really became so discursively focused, I picked up this book and I'm like, okay, why do people like this? And when I read this first page, I was like, oh, okay, that makes sense. You can make this immediate connection to Riemann integrals. Maybe a lot of people can do that. But one thing that I have seen from teaching is that a lot of students are not familiar with what the integral symbol actually is meant to represent. And so I didn't want to kind of guide us to there exactly, but it was one of the bigger things that I did pick up on, that if I'm trying to get students who just came out of undergrad to make a connection into this text, which says it was written for first year students, what are the things that I would expect that student to seize on? And so for me, it was the Riemann integration. So this bottom part where they start talking about measure, that actually gets discussed and taught, whereas the Riemann integral itself, that's not the subject of this chapter. It seems to be what is assumed knowledge on the part of the student. At least this is what I got from reading it. You guys may have maybe read this differently than I did. And my love of teaching calculus really came from the fact that it felt like that was the place where all of these topics that we taught students in K through 12 came together. And so I told them that this is the point where all the things that you learned, you are going to need to weave them together. So if you were taught them in a way that was disparate, it's time to make them a little bit more unified. So when I have taught Riemann integration, Riemann sums, Riemann sums, a lot of students really struggled with it. And do any of you have any ideas as to what they were struggling with, or guesses as to what students struggled with most when writing out Riemann sums? Think of high school.
Afraid of sigmas.
Sigmas. Okay, so what about
syntax?
What's the problem with the sigma? Like, what's the issue there?
It's new and scary.
You often have to write a sequence. So the subscript notation, you have to sort of like create items out of somewhere, and you have to understand how subscript captures that idea.
Oh my goodness, yes. So with the subscripts, when I teach statistics, there are some books that neglect the subscript. I have never seen this before. The limits of integration don't show up in the notation. Got it. So it seemed like the book thought it was easier for students if, in statistics, if we were describing how to do a standard deviation without subscripts, which I found to be just a little bit odd. So I went ahead and just taught the students that, and it made things so much easier down the line. But it seems like we sometimes pull out or take away some of these symbols in order to make things easier for students. But I have personally seen that it seems like it confuses them more down the line. I like that better. And there was also a hand, but I don't think that person got to talk. Was it Melfi was the last name, I think?
Yeah, it's okay. I mean, what I was going to say is sort of along the lines of what we're getting at anyway with syntax and words, because I have kind of a piecemeal background when it comes to things like real analysis, but whether it's this text in particular or what sometimes happens in people writing journal articles and things, is that you just get so bogged down in terminology that the text is just so dense with terminology. And I think Kate mentioned proper names in the text as well. That my first brain reaction is just like, whoa, what do I do with all of this? Which I think, we're also getting at with the syntax being scary because it looks different, or I have to take that extra time to pick it apart into pieces and figure out what each of the pieces means.
Okay, so I think that we're all in a pretty good place. I do want to make sure that we have time for discussion. So love what you guys are saying. I do have another task for you. So I'm kind of asking you guys to keep multitasking. I do now want you guys to do a brainstorm while I discuss part 2, which are the issues that I am potentially seeing with what we just read and with students in general. All right, so if you guys go back to your Desmos, the next thing, the slide before where you guys wrote your answers to your questions, you should see a slide that asks you to just brainstorm words that you think of or symbols or anything in response to function. It should be slide 5. And so you can do that while I'm discussing part 2 and part 3, and then we'll come back to that next. So you guys have an activity to work on to keep your hands moving while I talk. All right, so are we all clear on what we're doing now? All right, great. All right, so I will continue. So issues. All right, so we know that students have a lot of difficulty with mathematics, elementary school level, middle school, high school, undergrad, and these students also in graduate school. And there's a lot of concern over student attrition, particularly students who leave mathematics who are from underrepresented groups. So one of the ways that we try to address that is, well, figure out what the culprits are. Why are students leaving these fields? So one of the things that we might look at is instruction. Does instruction have some impact on why students are leaving? Are students not being taught well? And then if, let's say, we do have some innovative ways of doing instruction, can we potentially measure how well that instruction was by doing an assessment? Should we maybe look for student errors or misconceptions and then see if we can potentially rectify those? What are the reasons for the student difficulty and how can we potentially fix them? Okay. So one of the things that I have really started to hone down on was this idea of phases of curriculum. So we have our intended curriculum, which sometimes is what is written. What are we supposed to teach in, let's say, a course at the K through 12 undergraduate or the graduate level. The implemented curriculum is sometimes referred to as enacted. And so this is how the material is actually being taught. There is a potential for what or the way that it is being taught to be a little bit different from what was actually intended or written. So that is one potential place where we may see disharmony between what was intended and what was actually enacted by, let's say, an instructor. But then we now look at the instructor and then the student. So we have the attained curriculum, which is sometimes referred to as realized. So this is what the student has actually learned. And I really loved this particular portion of things because what students learn isn't necessarily what you have intended for them to learn, but hasn't learning still occurred. So I felt like we needed some sort of way to look at these three things if we're trying to figure out some of the possible reasons for student difficulty. Okay, so like I said, I believe that there may be a misalignment in curriculum. So how do we study that? So I thought that we would look at the instructor and the student at the same time. But in mathematics education, you will see a lot of studies that are only focusing on the student or only focusing on the instructor or just that classroom. But I feel like we need to actually examine discursive cycles. So what I mean by that is how were the students taught? What is the text of how they are assessed? How does the student interpret the text? How does the student think about the text of what they're being asked? And then what does the student produce, the product? That cycle is complete when the product is then read by the instructor. What I think has been happening and what I believe may be causing some students issues in real analysis happens at that calculus level. So what I think may be going on is that students are getting through calculus without any understanding of necessarily a Riemann sum. So they probably would not recognize it when they see it in like a book like this, because what they actually are interpreting in terms of seeing an integral symbol is something prompting them to act. And so it's very hard to go from this thing is prompting me to act, which for a lot of students is use these rules I have learned for doing integration. And there's a lot of skipping of where integration and even derivatives actually come from. So we're actually losing an opportunity for students to make that connection to their previous calculus or their introductory analysis course. So when I was saying what courses do you all think would have helped students with this? Sometimes students, people will say introduction to real analysis. Real analysis absolutely does discuss Riemann integrals. But one thing that you do not necessarily get a chance to do in introduction to real analysis is to do the sketches. One thing that I really try to do with students is to have them make connections that are mental. So what can they actually imagine? Mathematics at a certain point becomes entirely mental. So students have to imagine some of these things in their heads, and then in order for them to try to make connections to the higher levels of mathematics. So how do we do that if we're not attending to it? So they do recognize the rectangle drawings of Riemann sums, simply including a labeled diagram of, I absolutely agree with you. Oh my goodness. So I'm looking at what Andrew Cooper is saying in the chat. They do recognize the rectangle drawings of Riemann sums, simply including a labeled diagram of what f of t sub I is, what e sub I is, etc., would improve Rudin's exposition. This is also, though, an issue in calculus books, calculus 1. One particular, yes, I'm a picture. One particular issue is when students get to volumes in calculus 1. I think that that is a particular portion of calculus that should be taught in 3D. So there are certain things that it is very hard for me to get across to a student if I am unable to actually show them what it looks like. But I was talking to a student about volumes of shapes that have like a base. So we're talking about this, the base is, let's say, horizontal to the x-axis or something along those lines. And I was giving them the example of an aircraft hangar, like those little houses that you see like planes are parked in. And I was trying to let them know this is the kind of shape that they're talking about. And when they were describing the cross sections as being these semicircles, this is what this is. And it's a little bit different from the other volumes that you have been learning to calculate. But that's very hard to describe to students if you're not teaching it in 3D, and it's very hard to visualize it from books. And so this is one of the issues that Riemann sums of value, thank you very much. This is one of the things that I thought might be causing some problems for students. Another thing is that in that discursive cycle between the students and the instructor, sometimes students are in this age going outside of what is taught and they're looking online. So there may be some Googling, some going to Khan Academy, and I'm not sure if you guys have watched some of these videos on YouTube. they are not the best mathematical explanations. And our students are essentially being told that we are just making things hard unnecessarily for our students, and they are instead being taught tricks. But it's very hard to go further in the mathematics if all that you have for your course is a trick that you've learned. How are you then able to generalize? So these are some of the things that I have been thinking are going on, but what I wanted to do was study what are those ways students have made sense of these problems, because that's going to show us how to move forward. So here comes cognition. So anyone who actually likes this, this is when I really started to feel like I was able to really help students, and then to try to put it into research, because there were things that I could do naturally, but then how do I actually discuss that? Totally agree with the person saying being dismissive about conceptual understanding is silly. Totally agree with that. Totally agree with that. Like the thing that I tell students is that we don't want planes to fall off the sky. If you are going to be the person working on my airplane, I'm going to need you to understand conceptually the mathematics behind how this is being built. And wouldn't you also want the same thing for the people who are working on these things for you as well? All right. So Sfard's theory of cognition describes thinking essentially as communication. So cognition is a term that puts together cognition and communication. So it's a term that encompasses thinking or individual cognition and interpersonal communicating as a combination of the words communication and cognition. It stresses the fact that these two processes are different, interpersonal and interpersonal manifestations of the same phenomenon. Okay, so in this sort of view, the same way that a student may necessarily talk to us is how maybe they are thinking to themselves. And so for this reason, when I'm trying to study a student's cognition, I actually use their discourse. I use what is spoken, what have they said in the conversation, and then I go from there. I try my best not to make assumptions about how the student is actually thinking, but I focus on the words. So some of the main portions of cognition are discussing this idea of objectification, de-objectification, subjectification, and operationalization. So words like knowing, learning, understanding are really unknowable states. There's really no way for us to know those things about a student without looking into their minds. So what we try to do is operationalize these terms instead. So find ways to say something definitive that you can actually prove. Subjectification is when we kind of assign this state of being to someone based on something that they have done. So something like a learning disability, or saying that someone has a learning disability, how is that something that we know? That is an unknowable state, and yet based on something we have seen or have not seen, we assign this idea of a learning disability to them. So that would be subjectification. Okay, objectification is when we can take these processes or these ideas and you make them into objects. So things that have existed in the world, like let's say an apple, no matter what, if we can communicate with each other or not, that apple will still exist. However, if you remove from this object that I'm calling apple, this word I have assigned to it called apple, apple is completely communicational. We would refer to that as a discursive object. And the reason why we're using that term is to enable us to communicate. However, the advantage there is that apple actually had some object that we could see, that we could touch, that we could feel, that we could assign that name to. A lot of things in mathematics do not have that property. So it is very likely that when we are trying to communicate with each other about things in mathematics, there's a good chance that we may not actually be communicating about the same things. And so I believe that this is pretty much one of the main areas that we may be struggling with students. And it becomes even more interesting when we don't realize that it has happened. I believe that this is one of the big things that is preventing students from having an easy time in real analysis. This is just one of my thoughts. So in cognition, and this also comes from other parts of psychology, we have this idea of signifiers and realizations. So when I was reading that section of Rudin, there were lots of terms that I were using that were not expressed on that paper. But what I was doing was I was assigning realizations to things like the summation, measure, T sub I. Those were not things that were there, but these were realizations that I assigned to it. And students do this as well. Okay. So once we have these objects that are essentially discursive, things get even harder when we start making new objects from objects that were already discursive. Again, this is something that happens in mathematics. How easy or how difficult is it for us to describe something like an isomorphism? Is that something that we can point out to people? Do we have ways of pointing out to? Or is to something that is endless? I have to consistently illustrate this notion of to by having repeated sets of objects that have this quantity that we have this assigned the name to. It doesn't end. So again, this is something, the issues that we have in mathematics. They're not bad, but it makes it hard to communicate across a field. Okay. We talked about most of this. So one of the main parts of cognition is that we see mathematics as discourse. And what makes it different from other discourses is that there is the way that we use words. Okay, our visual mediators, so these are things like our symbols, our narratives, inclusive of endorsed narratives, which are things like theorems and definitions, and then our routines. Now, routines can be encompassing of word use, visual mediators, and narratives. But what I love about routines is that they are not only mathematical and scholarly math discourse, there's also the personal routine. So one of the issues that I have seen with students is that they have routines which may not necessarily align with scholarly mathematical routines. So word use is defined as one of the distinctive characteristics of discourses, and it's all about the keywords that we use. In mathematics, these are mainly, although not exclusively, the words that signify quantities and shapes. Visual mediators are those visual objects that are operated upon as part of this process of communication. While colloquial discourses are usually mediated by images of material things existing independent of the discourse, scientific and mathematical discourses often involve symbolic artifacts created specifically for the sake of this particular form of communication, like the integral symbol. Narratives are any sequence of utterances framed as a description of objects, of relations between objects, or of processes with or by objects that is subject to endorsement, so substantiation, proving true or proving false, with the help of discourse-specific substantiation procedures. Endorsed narratives are often labeled as true. Terms and criteria of endorsement may vary considerably from discourse to discourse, and more often than not, the issues of power relations between interlocutors may in fact play a considerable role. So this narrative here is referring to scholarly mathematical discourse, but students can also have personal mathematical discourse. Routines are repetitive patterns characteristic of the given discourse, specifically mathematical regularities that can be noticed whether one is watching the use of mathematical words and mediators or following the process of creating and substantiating narratives about numbers or geometrical shapes. So routines are composed of two things. There's the task and the procedure. So if let's say I gave you all this problem to do earlier, what I would want to see is what is your routine for solving this problem? You yourself have the task that you believe is necessary in order to be in fulfillment of the routine, and then the procedure that is supposed to execute for that task. This can also be different between students and their instructors. And so this is the reason why I have students draw those trees that you guys saw earlier. It's for me to get at the task and the procedure pairs that make up their routines. Okay, so I do see that we're running low on time. I'm sorry, guys. We had a really interesting conversation about Rudin. I probably should have cut that a little bit short. But I don't think that we're going to be able to get to the part that I really wanted to get to, were these things called the discursive maps. So what we did together were the evoked maps, which are subject to a particular problem. But then there's this idea of something called a discursive map, what I wanted you guys to draw for function, where we try to get at all of a student's uses for a term. So of course, for a researcher, that can be very difficult to do in one interview. How do you get at all of a person's uses for something like function? And what I wanted us to do later was all of their uses for integral, so that we could go back and talk about the Rudin again. But what we know is that for something like function, if I had you all do it, most of you would end up having something that was quite hierarchical. You would probably tend to have lots of examples of functions that you guys generalize to the highest categories. So things like polynomials, exponentials, things of that nature. Properties of functions is probably one other thing that you guys may have naturally put together in your maps. Examples may have been on your maps and things of that nature. But when we do the same task with students, their maps do not look like this. Student maps for things like function tend to have lots of procedures that they have needed to use in order to get through the mathematics in their careers. So you might see something like, okay, function for a student, and then they'll write one-to-one and then write the way that they test for it. They might write something about vertical line test, horizontal line test, things of that nature, or XY. So writing down an ordered pair would be something that tends to end up in things like a student's map that we don't typically see in, let's say, an instructor's map or a mathematician's map. So that has been studied very, very, very long. And so what I wanted us to do, which we won't have time to do today, is to do the same thing for integral, to see what is common for us as instructors, because for students, integral is typically just seen as a symbol prompting them to act in order to go ahead and use these formulas that they have for integrating that they have maybe learned in calculus. Maybe some students will define integral as area under a curve, but we don't typically see them talking about this Riemann sum definition in the limit process for that. So if those students do not have that and they're going on to graduate school, as it is a pretty small part of their mathematical careers, it won't prevent them from getting the grades that they want. That may be one of the things that is making them struggle once they get to these graduate courses. So I just love the conversation that we were having earlier. So I didn't want to stop it because there were some things you all were saying that I had not anticipated that I just loved. But thank you for giving me this opportunity to talk. I am here to continue to chat. I particularly work with Cognition on injective and surjective functions because we know that students struggle with proof and we know that students struggle with function, and yet somehow students are proving that functions are injective and surjective. Something there did not add up to me. And so I use the principle of cognition in order to look at how students actually approach these tasks, and surprise, surprise, it's purely discursive. All right, but thank you all. I am here for questions.
Yay. Lovely. I can hang out for a couple of minutes as well. So I have a question. I'm sorry if this is a little theoretical, but so you were talking about the apple and that some language sort of points to an object that we accept is real and exists and others might not. And trying to compare that with like realistic mathematics education as a theory where like the apple, I mean, I accept that the apple exists, but it doesn't really exist until I think of it as an object. And from that perspective, once I think of something built on top of apples as an object, now it's as much of an object as the apple was as an object to me. So is this like a meaningful divergence between the two theories, or is there some sort of alignment, some way to align that?
So without using that term apple, if you were trying to communicate with someone else about it, I assume you would point at it. Is that correct?
I mean, I agree with you that that would be one way I could do it for sure.
Or at least
trying
to assure that we are talking about the same thing. Perhaps we can point this out. The issue with the purely discursive objects is that we can't point these things out. So how do we determine when we're not talking about the same thing? So what we would do in those cases is there evidence or is there something indicating that we might not be? So the only way to really do that is to look at our uses of the term. So that's kind of more so what I was talking about. So that's what the theory that I use in order to study how students' mathematics in these abstract domains, how are they using these terms? Because that can indicate if there's a potential there for cognitive conflict. Are they potentially saying something that doesn't really align with the scholarly mathematical discourse? What I have found interesting is when a student is not potentially in alignment with scholarly mathematical discourse, but no one can tell. Like those are the most interesting cases to me.
Yeah, in terms of your big question about like one-to-one functions, yeah, I have definitely seen students be like, I know I'm supposed to start like this, and then this thing happened, and then we do this thing. I just don't have a clue why that would convince anyone that this function is one-to-one. So they totally understand the way, I'm not sure I'm using this word correctly here, but they understand the way the discourse is supposed to go.
Exactly.
But they have they are not personally invested. It has no mapping to their internal discourse, maybe.
Well, I want to maybe get philosophical on that, BK, though, is like, I mean, isn't that, so Tim Gowers had this project like 10 years ago where he and Ganesh Lingam, I think is the guy's name, wrote a computer program to generate first year style analysis proofs. So proving that the union of sets of open sets is open and stuff like that, right? And it does beautifully. Like you can't tell. He tested it on people, and like you cannot tell the difference between what a first year or second year college student, or whenever they take real analysis would write, and what this thing writes.
Yeah.
So I mean, I don't know, isn't that what we're trying to teach our students, is like how to proceduralize things, so that, I mean, like,
no, it's actually,
I mean, I don't know, like, that's a way of understanding, isn't it?
Well, so I feel like there are some teachers, especially in the K through 12 level. Okay, so I really want to talk about Schoenfeld. So Schoenfeld, as far back as maybe 1980, had been saying that students see mathematics as nonsense making, and he pretty much blamed it on the way that we school them, that it's our fault. It's our fault that students see this as nonsense making. And so they look for ways to make sense of nonsense and get the A in the class. And so what I try to do is look for what are those ways, what are they doing in order to meet our expectations, even though they feel as though this is nonsensical. So now maybe eventually they have these instructors who are really trying to get at the heart of the mathematics. But once these students get to college, it can be very hard to kind of break them out of that habit of, I'm looking for context clues that aren't mathematical, but that will help me to get to the answer. But then when we kind of start to probe them a little bit more on, well, why is this true? That's when we start to see that they're really struggling.
Yeah, I guess what I'm trying to get at is, I mean, to me, maybe it seems like it's not so much a question of whether is this like procedural, or is it like, if you can succeed in the discourse, then that counts, like, versus, some other deeper level of understanding, and more just like the discourse has different objects. Like I don't mind if my students proceduralize things, but I want them to proceduralize them, with a kind of the primitive objects of that procedure aren't just symbols on the page. There are things like, okay, I see that I have to prove a set's open, so I better start off my proof by writing let epsilon be greater than 0. Right? Yeah. Like, or whatever, right? Whatever there is appropriate to the situation. Like, I don't know. I mean, that seems like that's how I feel like I'm not confident that that's not how I understand mathematics. So
no, and I actually do not feel like this is bad. So one thing I didn't talk too much about was how ritual is part of the learning process. You start at ritual. So we can never really know if a student has fully de-ritualized their discourse or not, and if they're fully exploring. We don't know that. What we look for is evidence of de-ritualization. We look for evidence that students are adaptable. Are there other ways of solving this problem, or are students only capable of solving this in one way? So we typically refer to ritual as a routine where task and procedure are the same thing. And an exploratory or more exploration type of routine is one where the student can separate the task from the procedure. So that particular task has multiple procedures that the student can do in fulfillment of the task. So that's what it seems like I think you want for your students. But the former thing that you said with the symbols on a page will be indicative that their task procedure pair is one and the same. And so that's what we don't want, because then we'll see that students, they do not adapt when the circumstances that would make that task useful have changed.
Well, that's a perfect place to do our last little announcement. So just a reminder, this is our schedule for the spring. I'm hopeful we'll get to reschedule these two for special events this summer. Can we give a snap to everyone who is part of this year? And then give a hearty thanks to Bolanle Salaam for an excellent session today.
Nice. Thank you guys for bearing with me. I was just like, are they going to be able to work and listen? Because I think some people like to do things together. But thank you guys so much.
It was lovely. Thank you.